Good afternoon, everybody. Welcome back. Hope you had a chance to grab some lunch. We're going to get started with our next session on water, and I'm going to turn it over to Samantha McNeil with Trace Associates, who's going to moderate this session. So over to you, Samantha.
Thanks, Joe. Hello, everyone. Thanks for joining us for session 3. Like Joe said, I'm Samantha from Trace Associates, and I'll be the moderator for this session. So the topic of the session is water, as mentioned, and we have 5 presentations for you. I'll ask the presenters to please try to keep it to about 25 minutes so that we can leave some room for questions at the end. And if you'd each like to start with a brief introduction of yourselves, that would be great as well. And please remember to turn off your cameras and your mics when you guys aren't speaking. So with that, I'll introduce our first presenter. We have Bill Berzins from West Earth Sciences, and he's presenting on hydrogen sulfide limits detection and treatment. So I will turn it over to you, Bill.
Hi, everybody. And I'll ask you to just let me know if my sound is not working properly, and I'll just get my presentation set up.
Sounds good and looks good, Bill.
Excellent. And are you seeing the screen?
You just need to do the display settings swap.
Excellent.
Perfect.
Okay, very good. So let me get started. My name is Bill Berzins. I've been in the environmental water and wastewater business for about 40 years or so, I think. So I probably have met some of you along the way. Really what I wanted to do is get started with perhaps something most important, and that is the safety moment for this afternoon. A lot of us are under quite a bit of stress these days because of what's happening with West Texas Intermediate, what's happening with COVID, uncertainty around the economy. And so the safety moment, we have 2 safety moments. One, of course, is going to be H2S, and the second one is going to be about making sure that we take care of each other as we go through a rather stressful time for all of us. There's quite a few resources that are available now within the province for assisting those of you and your friends. So just make sure that you reach out to, I've basically given you a website, but if you go to Alberta Health Services, you'll be able to see a lot of information where people can reach out as you experience stress in these uncertain times. And I think one thing that's very important, I'm seeing a lot of caution fatigue out there. And I've heard people say, I'm tired of worrying about COVID and all these safety requirements and the social distancing and everything. Just make sure that you don't fall a victim of fatigue, caution fatigue, and take unnecessary risks. So now let's move on to H2S. So H2S occurs pretty commonly. A lot of you have taken H2S Alive trainings, and so you're well aware that it occurs with oil and gas operations, especially sour liquids and sour gas. It can also occur as a byproduct of microbial digestion. So basically you get a sulfates, compounds, a source of carbon, the right bacteria, and you'll end up generating H2S in situations where you get anaerobic digestion. That occurs quite commonly in sewer systems, but it can be also found in silos, sumps, pits, treatment plants, paving operations. So H2S still occurs pretty commonly. One thing that I was surprised when I really looked into what are the design standards if you're designing a system for treatment of water or containment of H2S in something other than an oil and gas operation. A lot of the design manuals went out of print long before the web was the source for all of us for this information. So it's a topic that I think it's important for us to renew and refresh each other on so we don't get caught with an unfortunate exposure or fatality. If you look at, and I took a look over the last 5 years at where the most common fatalities have occurred in North America, it can occur in a variety of industries. I've highlighted a couple of them that you might be surprised about. For example, in a restaurant application, grease trap bulk cleaning was a fatality for a worker that went in to clean the space. Confined spaces and water well situations, either a water supply system or water sampling confined space, hog farm utility corridors, removal of old sewer pipes. So there's a variety of places that it shows up. And so I'll talk a little bit about why some of these fatalities may have occurred in those situations. Back in 2004, Hendrickson analyzed a bunch of data from the 90s, and there were some findings that are pretty important for those of you around the room. 50% of the fatalities occurred for young workers in their first year of employment. And we all know that the most dangerous time when you're working in either a process industry or an industry where you're not familiar with the risks, the most dangerous time is probably that first week or two on the job. But certainly within the first year, half the fatalities that have been recorded in North America during that time period were for first year workers. And it was quite common in both waste management, petroleum processing, sewerage, manufacturing, and it really didn't discriminate on the basis of how large the companies were. Basically, it could occur in companies with small workforces or large workforces as well. So it really doesn't discriminate by industry necessarily, and it doesn't discriminate by the size of the company. So let's talk a little bit about what are the physical and chemical properties that help define or create that risk. First of all, it's colorless, it's flammable, and it's highly toxic. So that creates the risk around exposure. It's denser than air, about 1.2 times air. Density. So in other words, it will pool in low-lying spots, and it's important for you to understand that when it is released, it will be seeking a lower spot in the topography or in the piping system. It's slightly water soluble, it is explosive at the right concentrations, and its solubility changes with water temperature. So these are all conditions that will change, or changes in these conditions will change the amount of H2S that's released from water and available in the breathing space. One of the factors that's quite important as well is the pH of the solution. So if you look at this graph, and can you see my arrow?
Yes, we can.
Yeah, if you look at this graph, basically it shows the relationship between the amount of dissolved gas on the red line and the amount of hydrogen sulfide ion in the blue line. And it shows that there's quite a shift in whether the H2S is available to bubble out, i.e. the red line shows that at a very low or acidic place, the H2S, a lot of it is available to bubble out. And then as the solution becomes more basic, there's less H2S available to bubble out. So if you're looking at commingling, let's say water streams, and you have a water stream that's fairly basic, but you mix it with, say, an acidic blowdown from another process, then you may have a situation in which your water that does not have a lot of dissolved H2S may still have enough hydrogen sulfide ion to be released when the pH goes more acidic. So this is one of the factors that you have to keep in mind, that a change in pH over the life of a particular water stream or wastewater stream can make a big difference on whether or not you'll have H2S released and an exposure. So the bottom line is lowering the pH increases the amount that's available as bubbles or dissolved that can come out as bubbles, especially in turbulent conditions. Lowering the temperature also increases the H2S solubility, so there will be more available in a dissolved form in a lower temperature. And then of course, turbulence really affects the release of the H2S to the atmosphere. So if you looked at, and I remember I mentioned some of the original design manuals that are long out of print, here's some examples of where you could have a wastewater flow that may not have a high amount of H2S in the head waters or head space if you look at the left diagram, but by the time it goes through a variety of flow conditions that create turbulence, you'll get a much higher or much elevated level of H2S in the breathing space. So these are the types of conditions that you really need to think about when you're looking at the system design or the safe operation of a system. So the factors that affect it then are pH, temperature, turbulence, and obviously the amount of H2S or hydrogen sulfide available in the initial stream. Now let's talk about what levels are important in the workspace. H2S can be detected as levels as low as 0.5 ppb. When I was involved in the operation of the Edmonton composter, for example, we didn't have sensors to determine the level of odors outside the structure. We actually had an odor committee that would come by from time to time because we knew that some of the members of that committee could detect a sour smell at a much lower level than we could ever measure. So the level for first stage of detection is as low as 500 million ppb. Then you move up and talk about, all right, within sewer bylaws, what levels is H2S prohibited at, and what levels is it a restricted substance? So most bylaws in North America prohibit the release of H2S into a sewer and also limit the amount of sulfide that's acceptable. So remember that phase or the pH drawing I showed you earlier. Most municipalities know that they don't want to have a lot of hydrogen sulfide going into the system because that can in turn be released in a change of pH within the piping system. So the sewer bylaws are pretty strict, and they're also strict because once H2S enters into the sewer system in the headspace, it deposits on the wetted top, say, of a sewer. At that point, different bacteria, not the bacteria that generated it, but the different bacteria basically convert it to a sulfuric acid, which now starts to degrade the concrete within a sewer system. And then if you look at the other action levels that are available, you look at the levels that CUPE, for example, recommends to its membership. So many of you probably have workforces that are unionized under CUPE. And so CUPE recommends a pretty strict guideline for exposure over an 8-hour level or 8-hour interval. So CUPE recommends 1 ppm as the action level for an 8-hour exposure and 5 ppm as the peak over a short term. By the time you get down to where it's serious at any level detected, because at that point, unless you know exactly what the cause is and can take preventative action, you really have to take avoidance as an action. But if you look at the levels that are even more serious, you go to immediate danger of life and health at around 100 ppm, and at 1,000 ppm, it can cause cardiac arrest. So I've seen sewer systems where you pop the lid on a manhole and you can have levels as high as 1,300 ppm. And so that's why it's very important, especially in the sewer applications where you know there's a potential, to always be taking precautionary measurements to make sure that you're not popping the manhole and having a look inside and immediately experiencing a heart attack. So some of the key considerations for managing safety are make sure you identify the source of it. Is it coming from stagnant water or stagnant biomass? Is it coming as a result of an upstream process? Think about the conditions and assess the conditions downstream that can affect the release, including any chemical addition that might change the pH, turbulence that allows for a greater amount to be released, changes in temperature, those types of conditions that can really take a situation in which the H2S is not being evolved and suddenly make it available in the headspace in some of the areas in which you may have worker exposure. And then, of course, we're all familiar with the stages that the protection that you would implement. Start with both an identification of the source, make sure you have sufficient engineering controls to minimize the exposure, and then adopt operating protocols so you respond immediately. And those protocols include equipping the staff with the proper detection gear. So the treatment options basically are, you can chemically treat if it's dissolved, let's say, as a hydrogen sulfide ion in water. So that's where chemical treatment is often done for water. Or it can be physically treated if you have a dissolved H2S in a dissolved form that can be released through turbulence or aeration. So there's a combination of treatment technologies that are available. I'm not going to go through them on the purpose of this webinar because we want to make sure we cover a full spectrum of the issues around H2S. So I'll just give you, within the handouts, you'll see there's a variety of technologies that are available, everything from modular systems that strip and polish to pure chemical systems and combinations in between. So these are some of the technologies that are applicable more on treating H2S in water and removal for safety or for reuse. We also have a combination of technologies that are available for lower volumes, either lower volumes of water or headspace treatment. So I'm aware, for example, that sewerage facilities and collection system facilities in Alberta often will use carbon absorption for dealing with lower levels, nuisance levels of H2S as opposed to consistently dangerous levels of H2S. I'm aware of collection systems or conveyance systems in which hydrogen peroxide is used to also deal with the accumulation of H2S in the headspace. So there's a variety or a spectrum of technologies that are available, really depending on the level of exposure, the amount of certainty you need around the treatment and of the peaks and spikes. If you look at my first exposure with H2S was actually in a drinking water plant in the city of Beverly Hills. The drinking water plant was actually located inside the administration building. So on one side of the wall was a drinking water plant. On the other side of the wall were dozens of offices for workers that were not involved in the wastewater or the water treatment plant. So in this case, we used a scrubbing system to treat H2S that came from a drinking water treatment system. In other words, the groundwater that was being treated for the purpose of drinking water had elevated levels of bacteria in it. That bacteria within the sand filters could create H2S. And so we had a scrubber system to make sure that we could take any of the backwash waters and treat them so we weren't releasing any H2S inside the office building, basically. Horn River was an example of an award-winning plant for high volumes of treatment in British Columbia for the purpose of treating H2S out of water for the purpose of hydraulic fracturing. And then on the right-hand side, you'll see a project that I've been involved with where we've taken the Horn River technology and basically scrunched it down to a modular system that can be applicable for smaller volumes and more remote locations. So there's a variety of detection methods, everything from simple tubes that you might be familiar with, including Draeger tubes, and simple methods for testing the amount of H2S in the headspace, right on up to laser-based systems and fixed systems on the fence lines that might be, say, like a boreal laser system. And so there's a full spectrum of technologies available as well. What's really commonly used in municipal applications is the Autolog system. So that's one that provides a flexibility for both instantaneous measurements as well as tracking measurements on an extended time period. From a due diligence standpoint, here are the factors to keep in mind then. Obviously, H2S Alive training is critical for understanding how to react to situations and also what the personal protective equipment would be. We have engineering controls at the front end of the process before you get to point of exposure. So the engineering controls would be the measurement of water chemistry, for example, if it's a wastewater stream, an assessment of the pH, an assessment of flow rates, then what type of turbulence is involved or is available within the system to release it. This next factor then, of course, is detection equipment, whether you have a more active system, such as a Autolog device or a laser system for detection. And then finally, making sure that the workers are equipped with the proper personal protective equipment. So some of the lessons learned over the years are, it's important to identify the potential sources of H2S and the conditions that generate it. Understand how chemistry alters the availability of H2S to be released from water or into the air, and that's pH and temperature, turbulence. Understand how airflow changes and can redistribute H2S. Some of the fatalities that I referred to early in the presentation occur in mining applications, where a change in the weather pattern and the change in barometric pressure and change in meteorology can cause H2S to migrate from one portion of a mine adit system to another. And so being alert and being aware of how those changes in barometric pressure and wind speed and direction can influence the availability and risk associated with H2S. Address the root causes with engineering controls. Don't rely heavily on your ability to detect and evacuate and quit. Really look at seriously the amount of engineering control that can be put in place to prevent incidences that require detection and reaction. Ensure there's sufficient treatment capacity in place. If you're going to put an engineering control in place, make sure it's sufficient capacity to deal with the upset conditions that may be caused. Also, make sure the personal protective monitoring devices are appropriate for the application, calibrated and routinely used by the staff. And then finally, evacuate first, ask questions later. Remember, H2S at very low levels, H2S basically eliminates your ability to smell it. So don't ever be in a situation where you catch a whiff and make a decision that it's nothing, because that might be the last decision that you make. So thanks very much, everybody. Hopefully I kept things on time, and I'll turn the floor back over to you.
Thanks very much, Bill. There was one question so far, and I'll invite anyone else who might have a question to just type it into the question box on the right side there. The first question for you is, what would drinking water taste like if it has high levels of H2S?
Bill, can you hear us?
Yes, I can. Yeah, I was just looking, I was switching over, so I wasn't looking sideways. What would it taste like with H2S? Right, so what you're going to get, if anything, I don't know how many of you have had water with elevated levels of sulfates in them. So you're going to get a little bit of it'll be slightly acidic. There'll be a slight sulfate sort of taste to it. One thing that's really interesting is if you look at the sulfate levels that are acceptable within the Canadian drinking water quality guidelines, there is really no limit to the amount of sulfate, because as soon as you start to detect sulfate, it basically becomes unpalatable very quickly. But I've never drunk water with H2S in it, so I'll have to determine whether I would ever be able to safely answer that question from first-hand experience.
Very good, thank you for answering that question, Bill. I haven't had any other questions come in yet, but Bill's provided his contact info there if anyone would like to follow up separately after this. So yeah, if there's nothing else, thanks again, Bill. I will turn it over to our second presentation. Up next, we have Hafiz Shishti and Tahir Rashid speaking on phytoremediation, salicornia production with produced water. So I will turn it over to you guys.
Can you hear me, guys? This is Tahir Rashid.
Yep, we can hear you.
Okay, should we start it here then?
Yes, please.
Okay, I'll be using my screen, and can you see my first slide?
Yes, we can. You're not in presentation mode, but we can see it. So if you want to continue that way, that would work as well.
Should I click on my camera, or should I go like that?
It's up to you. You don't need to have your camera on, but we can see you now.
Okay, yeah, let's start it now then. So we will be, I will be presenting on behalf of EnviroTech Canada, and our office is based in Calgary. And my other fellow, Dr. Hafiz Chishti, is also with us. If something happens on this side, as I'm presenting from Lahore, Pakistan, he can continue from there. So my presentation is on the siliconia production by produced water. So produced water is a byproduct of oil and gas recovery systems, and the average water to oil ratio is 2:3, and the concentration, the total dissolved salts, is from 12,000 milligrams per liter to 160,000 milligrams per liter, which is 1.2% to 16%. So the SAR, which is sodium absorption ratio, is from 5 to more than 32. Oil and grease ranges from 25 milligrams per liter to 5,000 milligrams, which is 0.025 to 0.5%. Typically found in organic products of water, including the zinc, lead, manganese, iron, and barium, which are heavy metals. So how we can get rid of this produced water? There are certain options. One of them, which I know in Canada, is deep well injection, enhanced oil recovery, water treatment, including reverse osmosis system, which is very costly, and then a wetland treatment, which is sustainable and practical. Now let's talk about compare the wetland versus the deep well injection. So we will be looking after the energy consumption. So if we are using the wetland treatment, this is 0.06 kilowatt hours per cubic meter, compared to the deep well injection, which is 3.6 to 5.5. And if you look into the savings, it's a huge savings, 98.3 to 98.9%. It also reduces the CO2 emissions as we are growing plants in it, and it works as a sink. And then wetland also provide valuable habitat to migrating birds. So I will be introducing one of the world's biggest project called NIMR in Oman. So what they have done is they have used the wetlands to get rid of the oil, and they started the oil field requires 250,000 cubic meters per day of water to be treated. So they started with 45,000 cubic meters per day. System consisted of the passive water separators, and what they were doing is they used 234 hectares of surface flow wetlands and 300 hectares for evaporation ponds. Like after getting rid of the oil contents, they were taking all that water to those 300 hectares on which they have developed the evaporation ponds, and due to evaporation, they are trying to get rid of the water. So during 2012, they added 120 hectares, and the capacity went up to 95,000 cubic meters per day. So this project has been done by one of the German companies, and they are running it successfully. So it was a reed bed water treatment project, and the project was actually, what they have done is they have skimmed the oil, and as the concentration of the oil in this produced water was very high, which is like 400 milligrams per liter, and they reduced it to 0.5 milligrams. And So reduce the energy footprint by 80%, expected salt production of 0.21 million cubic meters, and the wetland provided a habitat to about more than 100 species. So that's how they are doing it. They're skimming the extra water. They, produce 200 billion barrels per day. And once the concentration was gone down to 0.5 milligrams, then the plants can be used to get rid of those hydrocarbons. So, is this the solution to the saline water? No, it is not. So what they have done is they are only treating the water for hydrocarbons, but the salt concentration is increased. So when the water was coming into the wetlands, its concentration was 6,080 milligrams per liter, and the outgoing water salinity increased up to 10,460 milligrams per liter, 59% higher than the untreated water, for which evaporation ponds are used, which I already talked about 300 hectares, to just evaporate the water, and in that way they were getting rid of that treated water, which is treated for hydrocarbons, not for salt. So what is the option? So option is, like I'm saying, if it is, as people are saying, the oil is black gold, so I will say that this produced water is a blue gold, and we can use it to produce certain plant species which can be further used for human consumption. So those ways are aquaculture, number one, and number two is the production of halophytic plants into the hydroponic systems or directly onto the soil by using this saline water. So how we can do that? So these halophytic plants, they are actually very highly, salt tolerant plants, and salicornia is one of them. And we will discuss about that now. So salicornia consisted of high salt tolerant annuals without salt glands. That's a little bit of a science behind it. The first work was started in 1980s in Mexico, in Sonora State, on the edge of the Gulf of California. And we have about 130 million hectares of land which can be used for salicornia production by using this, this salt-tolerant halophytic plant. Small projects have been already, done in United Arab Emirates, Egypt, Kuwait, Saudi Arabia, and Jubail. They have in Saudi Arabia, they use this water to produce, the fodder from salicornia, and that was fed to the cows. And I just want to clear here and make a point, as this is actually depositing the sodium into its tissue. This is a little bit of a salt tinge, and animals like it, and they were actually trying to export that fodder to other states from that particular project. So coming back to salicornia, salicornia is like in the Bihar project. I'm just giving the example of Saudi project. So this salicornia is rich in iodine, phosphorus, calcium, silicon, zinc, manganese, and vitamins A, C, and D. So in low salinity, the cell electropotential of salicornia, basically, the follow respond to the inhibitors in the fashion similar to the glyphosides, but when the salinity levels are very high, the process of dealing with these salts, which is chloride and sodium, is basically, it's a different way. Vaporization is that way of doing it. So I'll not be going into the detail of it. And so the halophytic species of Amaranthacea family is generally very, they have a high ratio of sodium and potassium. And then Salicornia dichorsosa, is absorbing the presence of absorb more potassium because of high, the sodium levels. And I will go to the next slide. So they have used different species of Salicornia, and they try to, germinate those plants into it. And on the column on the right hand, you can see, the concentration of salt ranges from 240 to maximum of 1700. So they selected those species and they try to grow those with the produced water. So now I will be doing a little bit of a comparison of the seawater versus this produced water, and the maximum concentration of the salt water, any salt water, where the Saliconia can successfully be grown. So if you look into the the salinity at Nimmer is at 10,000 milligrams, which is about 1% salt or 174 millimoles. Seawater is 3.5. Optimum growth of Saliconia can be achieved at 1.75% salt. So it shows that we can successfully use 1% salt, which is produced water, for successful production of Saliconia. Yeah, my screen is actually my computer is frozen. Dr. Chishti, can you go from there?
Hello, guys. Can you hear me?
Yep, we can hear you. Did you need me to switch screens to you, or are you just going to speak for now while we wait for the screen to unfreeze?
No, it's moving now. It's moving. Okay, I'll continue from here.
Okay, I'm muting my.
So the next table is, you can see that I have given the comparison of salinity of the seawater, produced water, optimum Saliconia growth, and brackish groundwater. So if you look into those columns, seawater 3.5, which is basically related to the previous one. Then we have produced water, which is 1%, optimum 175, and general brackish water, which is high SAR water of the groundwater, is 0.3%. So we can use this on both in hydroponics as well as on the soils. So how I can do that? So there are certain ways. In terms of aquaculture, refers to the cultivation of both fish and the plants. So the sequence is aquaculture first, like we have to use this water to rear our fish, and the excreta of that fish will actually enrich that water in terms of plant nutrition, and then we can use the same water for the hydroponic production of veggies. Enrichment of, so that's the process. And yeah, my screen is actually trying to, it is, can you refresh it or? Yeah, Chishti, I'm sorry, guys.
No problem. Just a little bit of a lag.
Again, so there are some slides, like we can show you the aquaponics, like first the fish, second goes to the biofilter, and then to the hydroponic system. And yeah, Dr. Chishti, you go ahead from there. I have some problem. It's freezing here.
Okay, we're going to switch to Hafiz's computer then.
Okay. I'm not sure if the presentation is already uploaded on my computer.
Okay, can you see my computer again?
Yes. Yes, we can.
Okay, I'm going back there, and my computer is working. So I'm showing some slides now. You can see they're producing it at a small level at greenhouses, and the bigger level then goes to the direct seeding onto the soil by using a drip irrigation system. Then this one is another one. This one is another one. And the Saliconia field production in Eritrea and Somalia. And now I will be talking about a little bit of the nutritional value of Saliconia. So if you look into this table, we can see that crude protein, ether, and then crude fiber, gross energy, and oil content. So if you look into that, crude protein is 340 grams per kilogram, ether is 64.5, crude fiber is 36, and gross energy is 19.4. And if you look at the oil content, it's very rich in oil content, and in protein, 26 to 33, and then protein is 33%. Oh boy. Okay, let me see if I can move it a bit. Okay, the next one is, that's another way of looking into that. So I have compared the siliconia with cottonseed and soybean. Siliconia has 26 to 33% fatty acids. Cottonseed has 15 to 24. Soybean has 17 to 21. And the majority of these oils are actually omega-3 oils, which is oleic and linoleic acids, 12 to 17, and then 76 to 80%. Then how we can market it? So look into these slides, and siliconia sprouts are basically used as a salty salad. As I already mentioned, that is a tinge of salt in it, and people like it. Next, you can see all those dishes here, and it has been, successfully marketed by different countries, and that's it. If you have any questions, I'm there to answer.
Thank you very much for that. So far, no questions have come in, but I'll just give people a minute there. And I think I see one. So the first question we have is, in the NIMR project that you talked about, why did the salinity of the water increase after it went through the wetlands?
Can you repeat the question, please? Like this project was basically going on in Oman, Muscat. So their aim was to get rid of the oil, and they don't have the solution to the outgoing, high salinity water. So we suggested this one to them, and then the similar, we are actually facing the same problem in Canada. The wait time for deep well injection, to my knowledge, is 48 hours to 4 days. So this is a good option, especially in the southern Alberta, where we have good temperatures. We can use this product to produce halophytic plants.
Very good, thank you. If anyone else has any questions, maybe type them in now, but if not, as mentioned in the last presentation, if you guys would like to follow up separately, the contact information is right there for you. So yeah, you can email and ask any questions you might think of later. I think that was the only one that came up, so thank you very much. With that, we'll move on a little bit of ahead schedule to the next presentation. So the next presentation is the Story Arc model remediating a gasoline impacted downstream site in central Alberta. And we have Brent Lennox with Waterline Resources presenting. So I will just switch it over to you, Brent.
Thanks, Sam. Are you good there?
Yes, we are. Dr. Tahir, you can turn your camera off.
All right. So thank you everyone for joining me today. And good afternoon. I'm going to take on a big topic, which is time. And we're going to look at how it affects environmental assessment and remediation programs. So I'm first going to go through the general concepts, and then we're going to dive into some specific example, specific example, which is a gasoline impacted downstream site in central Alberta. So I'm assuming that we have a kind of contaminant leaning crowd, environmental crowd here, but looks like there may be a good variety of people. But I think a fundamental concept that we've been applying and has seen an increased importance in Alberta has been the conceptual site model concept. So that's basically considering the source, the pathway, and the receptor when looking and thinking about contaminated sites. But there's, I think that we haven't talked enough about time, and by by time, I mean the importance of the actual timing of the assessment and remediation activities that you can complete, and then also time with respect to how long is it going to take to complete all these activities, and what is the trajectory for the long term. And I'm not the only one that's concerned about and thinking about time. It's been a certainly a focus with the regulators recently, and they're looking to typically ask similar questions in Alberta, which is what are the timelines for milestones, and what's the end game? What's the long-term focus of the program? So if you weren't aware, geologists like myself are absolutely obsessed with time. So if you get, I showed this picture of a campfire because if you get a bunch of geologists like myself around such a campfire, maybe get a few drinks into them, and you're going to be hearing deep thoughts about time. So here's my sober attempt at talking about the time with respect to the environmental investigations. So we have geologic time. I'll set that aside, but what I find interesting is that we have like kind of what I'm going to call human time scales, political time and corporate time, that are relatively short term, and those approaches are being used to address environmental issues, and some environmental issues can last for long periods of time, especially if there's active remediation, or in particular, if you're taking more of a risk management, natural attenuation approach, you're looking at much longer timelines than those human timelines. So I thought I'd take a page, pun intended, just full of bad jokes today, from fiction writing to try to illustrate how time affects and influences environmental investigations. So in fiction, a very common story arc that has been used for thousands of years has included having an inciting incident, something happens, the conflict is created, there's a crisis, but it's eventually resolved, all is good, you've finished your summer reading book. So I thought I'd take an example from some fun example that's totally not based on reality, of how to use this fiction story arc. So if you can envision it, I'll be sitting on my couch looking at a topographic map, thinking about the next mountain that maybe I want to climb. The day of the climb, the hiking expedition, you're going up that mountain and you're thinking, wow, I'm starting to feel like this guy. And then inevitably you're wondering, well, who should I blame here? Maybe it's my wife or husband. So that's the kind of the crisis phase, but you realize that you kind of have to live with this person for a little while. So might as well resolve things. It may be snowing, but at least you're almost at the top of the peak. And then finally you get to the top of the peak. All is resolved, all is well, and you're off to the next storyline, which is, how do I get down from the top of this mountain? So while I think that fiction and hiking stories help inform environmental and scientific reports, there are some fundamental differences. And I think a good scientific report should provide the evidence in the front to lead the reader to the same conclusions that the author has reached themselves. And it can't be fiction, right? It must be based on data. And so we can't, as scientists, we can't create the stories in the way that we maybe want them to. We have to let the data decide what the conclusions are. When I'm comparing scientific writing to, say, a hiking story, it's interesting to think that in the report, a scientific report, you're not talking about conflict and crisis. And there may be a lot of those hiking-like stories, those field war stories that may occur when you're doing the work, but you never really see them in the report because scientific reports are more factual, less emotional. So I thought it'd be kind of fun to try to propose my own story arc for environmental investigations. So in the most generic form, you have your spill and cumulative release, your phase one, which is like a background review. From that phase one, you start to understand, oh, there may be some issues that need to be addressed. So let's actually collect some data at the site, the assessment phase, where you really don't understand the issues and receptor risk particularly well until you've done a certain amount of assessment and you reach the point where environmental issues are reasonably understood, and then you kind of have a de-escalation of effort, a resolution that may or may not include remediation and risk management leading to eventual regulatory closure. So, and then, yeah, there's that generic example, but my mind kind of gets spinning about a bunch of other options. So in fiction, there's been some studies where they actually look at the story arcs and how many there are in a generic sense, and there's only 6, which is surprising. So I thought I'd take a crack at showing you that very generic one, and we'll go through a couple others as well. So the first one would be the over-assessment story, which is where the practitioner, I think, feels like they've never collected enough data to feel like environmental issues are reasonably understood, or perhaps it hasn't been, the objectives haven't really been thought of clearly. Number 2 would be the poorly planned, simple turn complicated excavation, where maybe not enough assessment was done, appropriate guidelines weren't considered, in particular Tier 2 adjusted guidelines, and as a result, the kind of rush into the excavation, and yeah, you may end up getting regulatory closure, but geez, it sure took a long time and it sure cost a lot to complete. And then there's also, on the flip side, when if things just go straight to risk management and no one's really critically thought about whether the guidelines apply and environmental risks, you're basically continually monitoring, but not really monitoring a site that maybe could be closed. And then finally, there's my favorite, which is the perfect consultant story, as maybe you've already seen in this conference, and that's where everything just goes perfectly, which is great for you know, it really does work for a simple site with minimal environmental issues, but as it gets more complex, that story arc may change. So today I'm going to talk about a kind of a situation where there's impacts, hydrocarbon impacts in fractured bedrock that is fairly close to a surface water body. So in situ remediation was completed. So I think we need to be realistic about these types of situations. They're relatively heterogeneous environments with, yeah, just fairly, where it's very hard to remediate. So I think I'm advocating for in each phase of completing the work, we need to think carefully about timelines and long-term plans. And we also need to, I think, acknowledge that the tail end, the risk management, is going to be a bit longer than you would see with that perfect consultant story. So at the start, we have assessment, which is just generally building into basically establishing remedial endpoints and also just getting a basic sense of what's up and what's down, what's the extent of impacts. And I think that kind of work can be done in fairly, you know, from year to year, but it eventually would result in a remedial action plan or a risk management plan. And then we get to the remediation phase, which is in the yellow, where I think we need to be thinking a bit more long-term. Yes, we have those 1-year budgets. We all, you know, you want to get your cost estimate approved for the next phase, but we also should be thinking about the long-term, which for human timescales is I think 4 years is a reasonable expectation for how far we can look ahead. So because eventually, yeah, the remediation is going to become less effective, and once we're getting to that tail end, we want to be prepared. We want to be thinking about 1 year, 4 year, and then maybe even, you know, the next phase, the risk management phase, what's going to happen in the next 10, 30 years. So I'm gonna talk about go into a specific example here, which is as the title implies, it's a downstream gas station in central Alberta. There's a relatively large volume gasoline spill on a commercial industrial property and the down gradient land use is residential, mainly residential, some commercial. The site's located approximately 150 meters away from a river. And so the geology, it's characterized by about 3 or 4 meters of clay underlain by sandstone with hydraulic conductivities that are very heterogeneous and variable, 10 to the minus 8 to 10 to the minus 4. And interestingly enough, the water table is quite deep, at least for Alberta. So it's 14 meters below ground level, and it's connected to that river. And so first things first is, okay, why are we doing this work? So looking at receptors each in turn, ecological contact pathway is less of a concern because it's in a town and it's a active facility. The protection of potable water was managed using and is currently being managed using administrative controls. So the town has bylaws to restrict potable water use within its limits. Vapor inhalation was looked into, but wasn't really at the top of the list. And then finally, the receptor that we were focusing on was freshwater aquatic life, because the impacts you could actually see in pore water at the riverbank. But they haven't been detected ever in surface waters. So that's what we focused on was the freshwater aquatic life pathway. So I'm going to go over this site. It's 10 years of history, maybe over 10 minutes. 10 minutes, I think I probably have left. So I've given away the story here with the story arc, but I think if what makes a story interesting is how you got there. So and then I also wanted to note, like, just for illustration purposes, I've tried to make it a bit more linear than it was. But basically, yeah, there were a lot of simultaneous activities that were going on at the same time. So there was first that gasoline spill that we talked about. The spill was reported. Another consultant came in with an auger rig and drilled a couple holes to bedrock and thought, well, is this clean? But there's a pretty decent volume of gas that was spilled. So where did that go? So Waterline went in and did some drilling and identified hydrocarbon impacts at the water table, which was relatively deep. And then subsequently took some pore water samples from the riverbank, and hydrocarbons were there as well. So it was then we thought, you know, this is probably a good candidate for remediation. So the first step was that the client was decommissioning their pump island. So the just biggest bang for your buck is to just excavate the soil. And so once that pump island was decommissioned, we went ahead with that work, and then wanted to address the impacts in groundwater. So multi-phase extraction was completed, trials were completed, and that method was selected because there is we know it's pretty well known that it works well for relatively volatile constituents that make up gasoline. The hydraulic properties appear to be favorable based on hydraulic conductivity tests, slug tests, and there's a little bit of LNAPL, not significant volumes, that made it favorable because we could deal with that LNAPL as well. And then finally, yeah, the hydraulic properties were good for containment. So maybe we can try to keep those impacts, high concentration impacts at the site, contained. When we completed the trials, we found that vapor concentrations were in the LEL range. So that means that you're getting some really good recoveries from the vapor phase, and the groundwater extraction yields were suitable. And then once again, I did simplify the results. Bedrock impacts in fractured bedrock are very interesting. Because they're so heterogeneous. So and we saw that in the trials as well. So the program then went into commissioning an MPE system on site, and it was active for 3 years and resulted in about 14% of hydrocarbon volume being estimated to be recovered, which I thought was pretty good. And we'll go into more about the MPE system later. The client also wanted to look at offsite impacts, so that were on those residential properties. So we couldn't use MPE system because there's a highway in between the site and those residential properties. And we didn't really have access to power, and wanted it to be a little less intrusive on a residential use for the remediation activities that were being completed. So we used peroxide injections, hydrogen peroxide as an approach, and this method was, the chemical in particular that was used was used because we didn't want something that was long lasting, that would potentially reach the river, and hydrogen peroxide reacts very quickly with organic material, so it was an obvious option. And then because we were so close to the river, while we were doing those initial injections, we were also monitoring field parameters, including dissolved oxygen and oxidation reduction potential, just to make sure that we weren't getting our injection chemical being daylighting into the river. And so we started with fairly low percentages of peroxide and higher volumes, and then as we became to understand the system a bit better, we relaxed on the concentration balances. So in total, 10 events were completed over the first two years, and then just less frequently, more targeted injections later on in the program, until we achieved our remediation goals, which were to meet the freshwater aquatic life pathway guidelines. So while we had some success with the injections, we did have, as you see with MPE systems in general, we saw a tailing performance into the third year. So we tried a bunch of optimization methods to try to get those recoveries back up, but they were ultimately unsuccessful. So we turned off the MPE system and just saw if hydrocarbon concentrations would increase. And what we found was that the hydrocarbon concentrations didn't really dramatically increase after shutoff. So I think we made the right decision there. But on the flip side, maybe MPE was starting to become less useful, but we still had on-site hydrocarbon concentrations that were greater than our remediation targets. So after meeting with the regulator about this site, based on a supplemental information request that they sent us, we decided to look at the on-site oxidant injections, just to kind of, I guess, in a way, polish the on-site concentrations to hydrocarbon concentrations so that we could meet those remedial objectives. And with the increased confidence of having the down gradient offsite peroxide injections under our belts, we could then focus on, we could do less frequent, higher concentration peroxide injections on site. So then we moved on to risk management. So the remediation program, I think, accomplished what they're intended to accomplish, and we were quite excited because after a while we'd done all this remediation work, and then started to see that the riverbank, the pore water samples that we were collecting at the riverbank were starting to have hydrocarbons less than surface water quality guidelines. So that was really good news, and allowed us to feel like something, that the remediation activities amounted to something, and also that the receptor risk was being managed. So then we got into more of a monitored groundwater monitoring, more of a monitored natural attenuation phase, and then just targeting those higher concentration wells, both on site and off site, to try to continue to do some good on the remediation side of things by completing those oxygen injections. So if you take a look, take a zoom out and look at what we accomplished, we had mainly assessment and remediation being completed at the start, where we were still trying to get a handle on managing receptor risk, and we're managing issues, but we eventually got to a point where environmental issues were reasonably understood and I think managed. So and that was culminated, I think, with getting these positive riverbank results, and then subsequent activities have kind of resulted in more of a resolution. So I think what I want to get across in this presentation is that it's, I think, really important to frame the objectives so that we understand why we're completing the work, and that we don't get lost in the details, and that we be realistic with what we want to accomplish out of remediation. And then secondly, we should let data drive our decisions and our processes. We should be open to reevaluating objectives, and particularly during the assessment and remediation phases. And then I also wanted to put a plug in for considering multiple timescales, thinking beyond the next year, and thinking ahead so that we can more effectively and efficiently manage environmental issues. And I think that is it. So thank you for your time.
Thanks very much, Brent. I'm just going to turn my video back on. If anyone has any questions for Brent, please type them into the question box in your control panel, and I will just start with the first one that I've seen here. Is peroxide effective for higher chain hydrocarbons like PAHs?
I think, yeah, it'll basically, I'm not a, there are people that know much more about all the different technologies, but peroxide it'll just go after it. My understanding is that it'll go after anything that is organic. So I don't see why it wouldn't have a problem with PAHs. But yeah, I mean, PAHs, you'll usually, for most contaminant situations in Alberta, you'll see them with hydrocarbons as well. So yeah, usually you're dealing with them the same, I guess, at the same time.
Thank you, Brent. Oh, I did see another one come in here while you were answering that one. How did you inject the peroxide, and how did you monitor the groundwater conditions while injecting?
So Sequoia Environmental did the injection work, but we had some basically a custom well construction to make sure that it didn't short circuit to the atmosphere. If you don't properly hydrate your seals, your bentonite seals, you do run the risk of having trouble with that. So I mean, yeah, it's like to actually inject chemicals is I think basically you mix a batch of chemicals, and then I wasn't directly involved with, I wasn't directly involved with the injections, but you basically just put them in at a reasonably high pressure into the wells. What I was involved with was more of the monitoring, right? So seeing how effective it would be. So we used downhole YSI's readings. So that's just that's a multimeter, and put them on continuous logging and then did spot readings on other ones where we weren't expecting as much of a response, and then just looked for trends, overlaid the timing of the injections with the field readings.
Okay, thanks very much. That was the only questions that came in, so we will move on to the next one. Thanks again, Brent.
Thank you.
Yeah, the next presentation we have is innovations in low energy water treatment using geotextile dewatering systems for the removal of challenging environmental contaminants, and that is with Tyler Anderson from Bishop Water Technologies. I will put it over to you, Tyler.
Sure. Okay. Thank you, Samantha. Can you guys see my screen there now?
We can see your screen, just not your camera if you were choosing to turn it on.
I think I will. See if you guys stick around.
Perfect, we got it.
Okay. So apologies for the long name for our presentation there, but glad you got through it. Okay. So yeah, my name is Tyler Anderson. I'm a project manager with Bishop Water Technologies and have a background in contaminated site investigation and remediation work in Western Canada. So I'd like to begin by briefly introducing Bishop Water. So we're an Ontario-based company that specializes in low energy, easy to use solutions for solids management, water and wastewater treatment, and removal of environmental contaminants on industrial sites or even on remediation sites, which is kind of the focus of this event here today. So among the key technologies in our solutions portfolio is the Bishop Solids Management Solution. So we'll talk about how it can be used for managing environmental contaminants here today. And I'll talk about that more in a minute. So we also offer biological treatment solutions, chemical conditioning systems, and ultrafiltration and aeration systems. And these are all kind of pieces that work together in these larger projects. We've worked closely with other technology providers and our customers to continually enhance this portfolio. And we're very proud of the economic and operational environmental benefits that this brings to the company. Okay, just going to move on to the next slide here. So this one introduces our solids management solution here. The main focus that we're getting at here with this one, I don't know if everyone's had a chance to look at the abstract or not, but mostly focusing on metal leaching and acid rock drainage. So the solids that are produced during a treatment of metal leaching and acid rock drainage projects can benefit by being filtered out in these geotextile tubes. So we're the distributor of the geotube product here. So this is quite common in active or decommissioned mine sites across Canada, and even some oil and gas sites as well, anywhere there's potential acid generating conditions. So we've used these systems extensively throughout Canada and on some very interesting and challenging environmental remediation projects. And this solution provides everything needed to remove solids and or soluble solids from a sludge and water and collect them in the geotube container, removing a significant portion of the water and consolidating the solids into a dry cake within the geotube. So in the top left here in that photo, you can see one of the geotubes, or top photo, sorry, there's a geotube sitting outside there. And this is about an average size geotube. So they're manufactured in standard and customized sizes, which is great for environmental projects that are, kind of range in available footprint and remote access conditions and that. So these can be quite small and easy to move around. So they can be up to 200 feet long, 120 feet in circumference. We've used the system for more than a decade. And in the lower left is a photo that shows our polymer system. So the geotube is usually used in conjunction with a polymer treatment system. And that helps to, on a number of levels, like for metal leaching and acid rock drainage issues, could be injecting various chemicals that help to control the contaminants. And then the polymer would help to create a flocculant that's filtered out easily by the material. On the right-hand side photo, there is a series of jars with various sample media. The one on the left is a raw sample. The one in the center is post-treatment of flocculated material. And on the right-hand side is a sample that's actually passed through the geotube filter. So you can see that the solids have been retained within the geotube and the clear filtrate has been produced by the process. So that's pretty much it for the system. Very simple, and that's kind of the basic component here. We're presenting this as a simple solution that's easy to implement in various locations. It's a lot more cost effective and easy to set up than other mechanical systems that would typically be used for the solid management end of this process, such as a belt press or a centrifuge or something of that nature. So as a result, the Bishop Solids Management Solution has very low life cycle for cost, and it uses little energy as well. Okay, I'm going to move on to the next slide here. Okay, a little bit more on the polymer conditioning. So you can see that top photo. It's an image of what the polymer system would look like, and these are typically mounted in a sea can or something if it's an environmental remediation project where there's typically not an extensive amount of infrastructure on site. Bottom image there shows a geotube with a fill port and another geotube beside it there. Okay, so once the solids or the sludge is treated and put into the geotube, we start to see the filtrate being released. And you can see in the images on the right-hand side there, this is the subsequent stages in the process. And once all the liquid has been released, we end up in the consolidation phase. So solids are continuing to dewater. In Canada, we benefit from a freeze-thaw period. So just like any frost activity or creating void spaces in the particulate that's inside these geotubes, and when the frost comes back out in the spring of the year at the thaw, we end up with void spaces, and any remaining water can freely move around within the geotube and can discharge readily, resulting in a more consolidated material within the geotube. We'll end up with slurry contents or dewatered contents usually greater than 20%. In Western Canada, there's a paint filter test is usually what's done to determine the whether or not the liquid content is substantial or if it's suitable for landfill disposal or hauling and that. So it's a good method to get past that paint filter threshold. Okay, so as I said earlier, we've been using geotubes for a wide range of dewatering projects. The technology has continually proven itself as a strong, reliable, and highly effective method to achieve our projected objectives. I just want to highlight a few of the features of the geotubes that make them so effective and of such interest for containing contaminants at industrial sites and during remedial programs. So not only are these containers ideal for dewatering projects, they're also used around the world for challenging shoreline protection, where they're exposed to debris, abrasion, severe weather, and more. In Ontario here, we're working with a few engineers on the Great Lakes shoreline protection. Great Lakes water levels are extremely high last year and this year as well, and lots of shoreline erosion taking place. So that's basically a testament to the strength of these devices. And I know from experience in the contaminated sites world, once something is out of the ground, we're not looking for it to escape and create another issue. So once it's in these, it's a secure way to store it. So yeah, abrasion and weatherproof. The fabric is also inert to biological degradation and is resistant to chemicals, alkalis, and acids. Second is a seaming technique. So these geotubes are made by Tenkata, is the geotube manufacturer, and they're based in the US. And they've developed an industry-leading method to create the seams of the containers that maximizes integrity during filling and operational life. The seaming process is so effective that the seam strength is actually stronger or close to the same strength as the material itself. Whereas others that have manufactured geotextile tubes, the seaming actually becomes a bit of a weak point. And these ones for environmental work, they would come with an HDPE port that has a bolt-on cap. So once the material's inside, they can be capped shut as well. Okay, and that's it for the discussion on the materials there. Let's talk a bit more about the metal leaching and acid rock drainage and applications for these systems. Okay, so these photos here, metal leaching and acid rock drainage occurs when sulfur-containing compounds in the surrounding rock mix with air and water to form sulfuric acid. This acid then leaches heavy metals from rock, which can leak out of the mine and pollute waterways. And this isn't always associated with mines, even highway projects. And it's quite common now for the engineering and design process to account for PEG or potentially acid generating material and to manage it accordingly. But in some cases, there's still infrastructure related projects that do require management of acid generating conditions. So unfortunately, acid rock drainage is somewhat unpredictable since it can start while the mine is in operation or long after it's been shut down. And of particular significance is the extensive amount of abandoned mines that Canada has and old adits that are just leaking acid and metal laden water in challenging and remote locations. So once it's started, these conditions are very difficult to stop, and you're either looking at expensive capping and remediation projects, or you can set up a treatment system to manage the discharge. Okay, I'm gonna move on to the next slide. Okay, so there's several ways to treat metal leaching and acid rock drainage issues, but the most common way is with lime to neutralize the acid and precipitate metals. An unfortunate side effect of this method is the production of large amounts of sludge. The sludge is heavy, bulky, large volume, costly to manage and dispose of, challenging to move off site. So with some specialized equipment and refined understanding of the chemistry of the water, we can develop a program to create the pH swings needed to pull the various metals out of suspension and create a lower sludge volume than what would be typically done just with lime. So that's the first step here, using the chemical conditioning phase. It could be done in equalization tanks. And then from there, the sludge that's generated in the equalization tanks would be pumped through the polymer conditioning system and into the geotubes where it would be filtered. This solution can dewater faster and requires far less control than a thickener. The photo on the right shows an example of a geotube dewatering cell at an acid mine drainage treatment site. So as you can see, there are multiple bags here connected to one manifold system. So all the discharge is going into this one geotube field, this geotube dewatering cell at the same time. Bags up on the top are connected while the bags lower down in the layers have been filled previously. So they can be stacked on top. This is a great benefit for areas where there's possibly a low footprint and a lot of, especially with lots of new project developments happening to there's a large focus on trying to reduce the footprint. And I think probably some people in attendance here have been through various phases of the environmental assessment process and realize how rigorous that can be, and any opportunities to reduce the footprint that our sites and our projects occupy is considered a bonus. Okay, so once these are filled, they can, as we talked about on a previous slide, they're very robust and well-built items, so they could stay on site for, as long as they need to at least dewater properly. And in some cases, they can be used to create structural components of sites, dams, dikes, berms, whatever. They could be covered with soil and reintroduced as part of a reclamation process, as long as the capping and that meets the local regulations and criteria for isolating contaminants. Okay. So this is a project example where this system that we just introduced was used for metal leaching and acid rock drainage. So this is the Omega coal mine acid mine drainage treatment plant and geotube dewatering facility. So this was used in West Virginia. The site has been using geotube containers for several years to dewater sludge produced by an acid rock drainage treatment plant. So there's an aerial view here shown in this photo, and it shows the geotube dewatering cell. So on the left-hand side, you can see the parallel lines. Those are all the geotube units. And on the right-hand side, there's filtrate being collected and more room in the cell. So the plant receives raw water at a rate of about 200 gallons per minute, 46 cubic meters per hour, and uses lime to raise pH from about 2.5 to 7. Chemicals are also used to capture heavy metals and reduce the concentration from about nearly 2,000 ppm to less than 4 ppm. And these can all be customized based on the specific contaminants at a site as well. So the treated effluent from the plant and from the geotube containers is discharged to the local receiving body. And that's a big part of the consideration too when we're doing treatability tests and developing these projects, is what the local regulations are and what the client's discharge objectives are. Okay, so on this image here, we see a geotube application at the same site. This is a ground level image here, and this is showing the winter conditions. So with the right conditions, operating 24/7, these things can be run continuously through all climates. So it's definitely a valid consideration for northern applications here in Canada. Sludge is being continuously produced and pumped into the geotube bags. Because of this, the active bags don't freeze and are able to be filled and provide dewatering throughout the winter. Once a geotube is full, it can remain in place to continue dewatering and consolidating the solids. At that point, freezing is no problem and provides benefits, as we talked about earlier, as the frost opens up and the liquid can come out. So one interesting thing about this operation is that the site is currently participating in an innovative research study to reclaim rare earth elements from the dewatered sludge. So researchers have found evidence through their sampling and believe that the sludge contains high concentrations of rare earth elements, which when harvested could be worth more than $800,000 per year for this application. So this was really just in place to prevent environmental contaminants from being discharged to an adjacent water body. They knew that they had a problem. They needed to address this problem. When they were collecting samples to figure out what to do with the material in the geotubes, they started to realize, hey, there's a lot of valuable content in here that previously was difficult to collect and to consolidate. So they've ended up with a bit of a win-win situation in addressing their environmental issues and collecting a valuable resource. So the next slide here shows an image. This is actually the downstream situation before and after the acid rock drainage treatment system was implemented at this site. So what was once a polluted river, visibly laden with oxidized metals, is now clear and clean. Unfortunately, there are thousands of abandoned mines throughout Canada and the US. Many of them are suffering from some level of acid rock drainage and may require treatment into perpetuity. So with this reality ahead of us, it's important to find treatment solutions that are reliable, simple to use, and offer a high level of automation and are cost effective. So this is another example of a geotube set up at a gold mine. In this case, the pH is adjusted to precipitate metals and capture solids. And this is a 202 hectare site, and it was active for about 100 years, producing gold and arsenic. It was abandoned in 1961, and it wasn't until the early 1990s that remediation began. The Bishop Solids Management Solution was key in part of remediation of Young's Creek. So there was a nearby adjacent water body that had been impacted by the mining activity. Sediments were heavily contaminated with metals, primarily arsenic, or arsenic was one of the main contaminants of concern in this case. Sediment from the creek was dredged. It was treated with polymer, pumped into the geotubes, and allowed to dewater. On this slide, we have a table showing the contaminants of concern that were analyzed from this site. You can see the raw parameters as well as the filtrate parameters, and the final column on the right shows a reduction in percentage. So you can see that the filtrate quality was in very good condition after it came out of the geotubes. 99.9% reduction in the TSS, so a lot of the metals in this case were suspended, were not soluble. Heavy metals were also retained in the geotube, with most experiencing a 99% reduction or more. The filtrate from the geotube was much easier to treat before final discharge. Okay, so aside from the performance advantages that we just looked at, the Bishop Solids Management Solution also offers tremendous versatility. It can be installed as a temporary solution to address a project-specific application like the Young's Creek remediation project we just looked at, or it can be a part of a permanent facility like the Omega Mines Sludge Management Project, which is an active situation, and they have this discharge ongoing regularly that they need to deal with. So it can either be set up as part of a planned remediation, that has a defined lifespan, or it can be attached to an ongoing operational asset. In either case, the equipment can be housed in an on-site building, very versatile, or it can just be set up in a shipping container or a trailer. Regardless of the configuration, the system can easily be scaled up and customized to accommodate the site-specific conditions as required. Okay, so this is an example of batch treatment at a gold mine. So in this case, backwash was run through filters, cleaning the site's filters, and sludge is produced during that phase. The ferric coagulant caused sludge to accumulate in the filters, and a cleaning cycle, which occurred every 45 minutes, took care of this, but it produced about 1,900 liters of sludge each time. So the sludge was sent to a mixed tank for storage and treatment. We designed a compact system to treat and dewater the sludge, set up the Venturi emulsion polymer activation system along with small geotubes in a roll-off bin. So these were ultra portable, easy to get in. Once the contents are in them, the bins and the geotubes that are inside the bins can be moved out as one unit. Very easy to collect and move. The system pumps sludge from the mixed tank in a batch process, does it with an organic polymer and polyamine coagulant, and pumps it to the small geotube. Initially, the filtrate from the geotube was sent to a weir tank to await testing. In this case, the test results were good enough to discharge directly, so the weir tank was not necessary afterwards. And this is a slightly different example here. This one is related to a wastewater treatment facility that incinerates biosolids that are produced. The fly ash that's produced during this process, they had previously been storing it in a lagoon system direct from the facility. It wasn't a very effective mechanism for handling this type of material. So we came up with a plan and a design to use geotubes and a polymer conditioning system to do this. And this has been in place now for a few years, and we actually won 2 different awards for this one. This is the Greenway Pollution Control Plant in London, Ontario. And it operates year-round right through the winter as well. Okay, this is another active gold mine that we have this set up at. Yeah, and we wanted to highlight the winter aspect of this. So I know it feels nice and warm, good summer day, but I'll show you some pictures of snow. So this is a much larger permanent sludge handling system. This particular site uses a large pond to collect processed water and tailings. A conventional treatment system is also on site to remove arsenic from the processed water by precipitation, but it produces a lot of sludge. And the site was pumping and storing that sludge in another pond, but as the pond filled with sludge, they had to make a choice on how to manage it. So went with the Bishop Solids Management solution here, and included a large dewatering cell, multiple geobags, and they can be filled simultaneously through a manifold system. And the manifold system just means that we can select which bag it's going into, back and forth between geotubes. As one reaches its fill capacity, we can switch over to another one and let that first one dewater a little bit and reduce in height, and then go back into them, so we can really maximize the overall capacity there. Okay, and we talked a lot about metal leaching and acid rock drainage related work and other contaminants, but oil refineries as well. These have also been very useful tools for oil refineries, and we have used them as well on train derailments where crude oil was released into natural water bodies. Organic material or heavy hydrocarbons can have an affinity for fine soil particulate sediments. So in these stormwater ponds, the hydrocarbons often are affiliated with the sediments at the bottom of the facility. So during dredging projects, the sediment will contain a certain concentration of hydrocarbons, and when it's passed through the geotubes, because the hydrocarbons are already somewhat attached to the soil particles, they're likely to stay inside the geotube containers here. So we found that the filtrate that's produced from these situations is also cleaner than it would be if it was just moved straight through. So this is an annual clean out of sludge storage from tanks that hold process waste. And these are, in some of these cases, we have these set up and we would go back annually and just remove sludge and continue to top up the geotubes. The photo at the right shows an example of this type of system with lined geotube dewatering cell in the foreground and a mixed tank and polymer trailer farther in the back, just to the right of that red tank there. Okay, next couple slides are focusing on what we do in advance of getting out to a project site. So the bench testing, the treatability testing phase of the work. So for a metal leaching and acid rock drainage type site, we would request that we have an opportunity to either visit the site ourselves and collect representative samples, or have consultants that are already actively engaged with the site collect samples and bring them to us, to our lab. We have a lab here in Renfrew, Ontario, and we also do mobile field testing as well. And the treatability phase really has a lot of impact on how the overall project goes. We gain a full understanding of what the baseline water quality is like and what sort of treatment requirements really work best for the given situation. So this slide here shows an image of one of our lab technicians working on some sample material. Our next big challenge is to collect as much information as we can about the site, the material we'll be treating, and any treatment process that are ahead of the dewatering steps. So this is important to ensure we account for the treatment challenges that might be brought about by the material variability, process upsets, seasonal changes, etc. And finally, selecting the best polymers and designing the polymer conditioning process. So we start this process in our lab. The goal is to test the sludge and water and select the best polymer to retain contaminants and solids in the geotube, so while enhancing the dewatering process. We have hundreds of polymers to choose from, lots of experience working with different contaminants, different types of materials, so we have a good idea what polymers are going to work best, and also considering availability and access to getting materials to and from sites. But taking the time to test polymers and optimize the dose makes a big difference in dewatering performance, which translates into savings overall and possibly less polymer being used in the field. Another couple images of raw sample, and then with a 0.5% solution mixed in to the waste, you can see separation occurring on that image on the right-hand side. And of course, it's more visually obvious for samples like this that have a high solids content to begin with. In this photo, we're doing a rapid dewatering test. So a conditioned portion of sludge is poured through an RDT, a rapid dewatering test funnel system, and inside that funnel is a small piece of the geotube, the GT500 fabric. So the solids, after they're conditioned, will be retained on that disc of GT500 within that RDT tube. And this image shows, oops, sorry, I guess I missed that slide. I have my notes open on the side here. So that's the tube, the RDT tube there in that image. And on the next one here, so this is a view inside, and photo of the cake inside the tube, and then after the top portion has been removed, you can see the dewatered cake sitting right on top of the GT500 on that bottom photo on the right. So waste stream 1, after 1 hour, we're up to 20.4%. After 24 hours, up to 24.35%. And this is the percent solids content. So you can see the effective dewatering. And this is just an example of the type of information that we would produce and we would be looking for a dewatering component to a project. Okay, now in this sample here, there's obviously less solids. The RDT test also gives us a sample of the filtrate, and you can see in the example that the polymer and filter did a pretty good job of retaining the particulate material. We can also test for metals and other contaminants to gauge the potential performance. From here, we can proceed to other tests, such as a geotube dewatering test, which is similar to the RDT test, but uses a miniature geotube bag about the size of a couch cushion. And prior to proceeding to full scale, we would usually recommend on-site pilot testing as well. And this is something we would do if, if it's a major large-scale remediation project or an operational installation as well. Obviously, if it's an emergency response type situation for a spill, we do have the equipment and capabilities to just get right out there and take care of that stuff. Okay, so why choose the Bishop Solids Management Solution? I'd like to conclude with a brief summary of the Bishop Solids Management Solution for ARD treatment and sludge management. As you've seen, when compared to clarifiers, sludge thickeners, and even mechanical dewatering devices such as belt presses or centrifuges, the Bishop Solids Management Solution is much simpler, offers greater flexibility, and consumes very little energy. It can also potentially replace clarifiers altogether, as we've seen by the filtrate quality that's been produced. As we see earlier, a much smaller equalization tank could be used instead, and once full geotube containers can remain on site to store solids as part of a permanent containment system or temporarily until the solids are removed for disposal. And part of the treatability testing that we were talking about earlier too is really refining that chemistry to a point where we can produce as little sludge as possible. We know that removing and disposing of sludge is one of the most largest financial aspects to some of these jobs. So throughout our 20-year history of this system, we've seen time and time again that when we collect the appropriate data, perform the required tests, and design a system based on validated parameters, the system works very well. So we're very confident in the Bishop Solids Management Solution, that it can provide reliable dewatering performance depending on the material treated, and can quite often produce effluent that's suitable for direct discharge to a receiving body. That's it. So I'd like to thank you for your time and hope you found this information helpful. If you have any questions or would like to discuss your project needs, you can feel free to contact us with the contact information there. And I think it's also available through the EnviroTech agenda and conference organizers. Okay.
Thanks very much, Tyler. That was great. We do have a couple of questions here right now if you are able to spend a few more minutes answering.
Sure.
So yeah, the first one is, has there been any work looking at selenium for these coal-related applications?
Yeah, that's an interesting question. We've actually just been looking at selenium on another application. It wasn't related to a coal application specifically, but it is something that we're considering. Now, selenium is notoriously difficult to remove, but as with other metals, it does produce its own sludge when it is precipitated out, and it can come out with other metals as well. I did see that Kevin just joined back on here too. If Kevin's listening and has anything else to add on the selenium, you're welcome to join in here now at the question phase. But yeah, that is certainly something that we've been looking at, and we have done some testing. So if you had any specific questions about selenium, we'd be happy to talk about that offline. Yeah.
Great, thank you. There's a couple more. What's the lifetime of the system? Does it require replacement after a certain time of constant use?
Well, the geotube component of the system, they would be sized based on the flow and the expected sludge or solids production. So those would have a finite lifespan based on those specific project parameters. The other components of the system can be, we've built these systems, the polymer conditioning system, the chemical treatment systems, so that our field people can use them. So we also, I guess there's kind of two lines to the way that we work. We have our own field technicians that go out and do this work, but we also set up these systems at fully operational sites. So we try to make them as foolproof and simple to operate and durable as possible. And we've had a lot of really positive feedback about that. So I don't know if that answers the question. There's kind of two answers, I guess. The geotube components have finite lives, and the material, once it's used, the polypropylene part of the geotube is single use, so it would be disposed of.
Okay, very good. And I think there's just one last one here. How does the system sediments heavy metals into sludge? Does it work for any metal contaminant?
Okay, yeah, various metals will precipitate, well, actually, I guess it depends too. So you could have total metals or dissolved metals in your contaminated water source or your slurry source. The total metals are fairly easy to pull out with the suspended solids. Dissolved metals are a little bit more tricky, and that's where we do the defined treatability testing in the lab. We would do baseline testing, figure out what the concentrations of the dissolved metals are, work with various chemical components and pH adjustments. Different metals are going to come out of solution at either a high pH or a low pH. So depending on what we have in the baseline water chemistry, we may have to do 2 different pH swings to get all of the metals of concern out of the sample or out of the waste material. Did I cover that one?
I think so, yeah. But as Tyler mentioned, if anyone has further questions, please contact Tyler or Kevin at the info that you see on the screen. And
Samantha,
with that,
sorry, I do see one other question from Bill here. It came through the chat. Are there special restrictions for disposal of spent geotube that may have accumulated metals that would precipitate during drying? Yeah, I think if you were dealing with concentrations of metals that were substantial or even potentially leachable as well under landfill conditions, you would probably do a toxicity characteristic leaching procedure on a portion of that geotube if it did have a substantial amount of solids retained within it, just to make sure you're in complete compliance with local disposal regulations. But otherwise, yeah, it is a polypropylene material which is recyclable. So if you were able to clean all the metal, the soil and the metals out of it, it technically would be recyclable if the facilities would be able to take it. hope that answers your question there, Bill. I think that's it. So thank you
Okay.
very much.
Perfect. Thank you so much. We will move on to our last presentation for this session. So we have Alicia Sorty speaking on lessons learned from the Christie Park Community Drainage Improvement Project, design to post-construction. So I will turn it over to you, Alicia.
Thanks. Can everyone hear me okay?
We can hear you, and I'm just waiting for your screen to come up. There we go.
Okay.
Perfect.
Great. Okay, so hi everyone, thanks for joining. So I'm going to be talking about a project that I was working on with Dillon Consulting. It was part of the Christie Park Drainage Improvement Project, and one of the improvements specifically that I'll talk about is the Strathern Dry Pond expansion. So just a quick overview of what I'd like to present today. So I'm going to talk about the existing stormwater conditions, minor system, and then also major system trap low that we were looking at, historical flooding in the area. I'll talk about our pond design that we did for our retrofit of this dry pond, lessons learned, and then show some of the construction and post-construction photos. So this project was located in southwest Calgary. Strathern Crescent is within Strathcona Park community, and pretty much 17th Avenue, and then just west of Sarcee Trail. So the catchment area that we were looking at with our stormwater model was around 790 hectares. It covered 4 different neighborhoods on the west and the east side of Sarcee Trail, and then also included Sarcee Trail. With this project, our main objective was to increase the level of surface within the minor system from less than a 2-year event, which was currently experienced in some areas of the system, to a 50-year 4-hour event. Yeah. So this just here shows you the minor system and level of service of the minor system. So you can see areas in red right now are experiencing a less than 2-year 4-hour level of service. Areas in orange, less than a 5-year 4-hour level of service, and so on. So the areas that we really wanted to zone in on are those areas in red. So any of those pipes, catch basins, manholes located within those areas of red were areas that we wanted to improve. And then just a zoom in of the minor system here. So when we modeled our 5-year 4-hour event, we actually saw a surcharge to surface at a few locations along Sarcee Trail, and those are shown by the red asterisks in the figure here, just on the right. And then, as you can see, quite a few segments of the piping system along Sarcee Trail were actually, flooding. So definitely presents an issue when you have vehicles traveling along Sarcee Trail. You've got spilling from these trap lows. And then when those trap lows extend along both of the driving lanes, then you have issues for public safety and then also for emergency services. So if both driving lanes of Sarcee Trail, northbound and southbound, are flooded, then how can emergency crews, fire trucks, police, ambulance actually go through safely when the road is flooded? So just to zoom in here from Google Map. So we had trap low issues. So trap low depths of more than 0.5 meters. And then the drawing, I guess the map just here shows an aerial of the surcharge to surface locations along Sarcee Trail going northbound. So that was a major area that we wanted to improve with this project. One other area that you see here in blue along Strathern Crescent that I'll talk about is a trap low along this residential road that also was providing some grief for residents in that area. Okay, so just talking a bit more about that Strathern Crescent trap low. So the trap low ended up being just under 5-meter deep trap low, but it was at a T intersection, so it made the entire roadway impassable. And during heavy storm events, it actually flooded up the road, both lanes, and then also spilled into this dry pond area that was within the transportation utility corridor you see on the right. So on August 4th, there was this severe thunderstorm warning between August 4th and August 5th, 2015 that ended up causing flash flooding within the city. Environment Canada noted that Calgary received around 75 to 100 millimeters of rain and hail over that period. So this area of the city was hit really hard and caused some flooding for the area. And I've got a video to show you as well. Let's see if I can do the video. Okay, let me know if the video is playing.
It's playing.
It's playing? Okay. Oh, it doesn't play when I expand my screen here. Okay, so just wanting to show you, I guess, the amount of water that was flooding this T intersection right here. So impassable to cars. Residents were kind of trapped during that time, and then you do have water spilling over the standard curb here on the boulevard where that chain link fence is and going into the storm pond. So definitely a safety issue. So what we were tasked with at Dillon Consulting was to come up with a revised dry pond. So there was an existing dry pond within that transportation utility corridor, but it was undersized for the flows that were coming to it. The existing volume was around 3,300 cubic meters, but based on our modeling results, we determined that we needed a larger volume to store. The existing pond did not have an emergency spillway, so that, again, safety issue. Our revised design, we ensured that we had an emergency spillway draining east towards Sarcee Trail. As far as the design goes, the pond was lower in the middle, existing pond, and then drained to like a 300 millimeter under drain, which then connected to the Sarcee Trail stormwater piping system. So we revised our design a bit just so we could have everything sloping towards the south, just to give us a bit more volume. And we also introduced a high flow bypass, so a 1200 millimeter concrete storm inlet that would actually divert water from the storm system into the dry pond during those high flow events, just to alleviate the pressure on the system downstream along Sarcee Trail. This part of the city also has a regional pathway running through it. So we ended up revising the original pathway, and then we improved, I guess, access to the pathway because we now provided 2 paved pathway accesses for residents, whereas before there was only 1. And so just to give you a little idea of what the existing pond looked like, so you see here, large, I guess, super CB catch basin in the middle. Everything's graded towards the middle, and then we have our pipe outlet going out to, I guess, the south, which is your left, and then that connects into the existing storm system. Our revised design, as you can see here, we have everything sloping towards the south, where our pond outlet is located, also connects into the same piping system downstream. We have a pond inlet, so that high flow bypass, also down here in the south part of the site. Revised the pathway, so we've got 2 accesses, one at the north, one at the south, and then we allowed for a maintenance road. So city maintenance vehicles, hydrovac vehicles could actually drive into the pond bottom to clean out the pond inlet and pond outlet as needed. Great. Okay, so as far as the construction phase lasted around 5 months from March to August 2017. We did require a pathway detour during that time. So pedestrians, cyclists were detoured along the roads. And then we did allow for 2 growing seasons for landscape maintenance. So we wanted to make sure that the areas that we disturbed that were seeded were able to grow back. I should also note that this area is an off-leash dog park. So in order to help ensure our landscaping had the best chance possible of thriving and surviving, we actually fenced off all of the pond areas for 2 growing seasons, just to make sure that we had adequate coverage. Total cost of construction was around 1.7 million. So going into lessons learned. So first lesson learned, I would say, is public engagement. The public here, we had some very vocal residents who had also experienced what I would call disruption fatigue. You know, they had lived through quite a bit of construction living in this area, and when they saw our construction vehicles coming to site, you know, to set up, they were a little confused. So this part of the city, there was the West LRT construction close by, and that took place between 2010 to 2012, which caused disruptions for residents. There's a high pressure ATCO pipeline that was upgraded in 2013 that also closed off their beloved dog park and provided some traffic disruptions. After the West LRT construction was completed, there was post LRT construction landscaping for 2 years from 2013 to 2015. And then with this project, we came in 2017 to retrofit the dry pond. So there were some residents that were not happy to see their beloved park off-leash area closed off yet again. So if we had known prior to our design construction some of the issues, we may have been able to better inform the public of what was happening and gotten them more on our side, because once they saw construction vehicles coming into site, yeah, they immediately called 311 and were not very happy. Also, it would have been nice to gain some more historical evidence of drainage issues in the area that we didn't have that clear of a picture of. So we knew about that 2015 storm event, but actually in 1996 in July, there was a very large hail event that actually caused a lot of flooding because there were orange-sized hail that hit Calgary and Winnipeg. And then the hail was so big that it clogged the storm sewers, catch basins, and then caused lots of flooding, as you can see from the photos down on the right. So residents did have some very important flooding concerns, and they just wanted to ensure that the project that they were going to be living through the construction phase of was actually going to alleviate their concerns. And I will say that it actually did. So for this specific trap load, this is that T intersection, Strathern Crescent. Because of the high flow bypass into the dry pond, we actually alleviated flooding in this area. And residents were actually very happy at the end of the project, but during construction, some not so much. Lessons learned number 2 would be utility locates. So I think it would be important for future projects to engage a third-party locate company just to ensure that we have addressed and identified all of the possible utilities buried above ground in the area. So within the transportation utility corridor, there's the 400 millimeter high pressure ATCO pipeline. And then during our design, we didn't have a clear understanding of how close this high pressure gas line was to our proposed pond realignment. So our initial design, as you can see below here, had our maintenance access road and pathway going into the transportation utility corridor. You see this black line kind of below that yellow one. That's the edge, west edge of the right-of-way, utility right-of-way. And when we showed our design to ATCO Pipeline, they said that it wouldn't be allowed because we would be encroaching. We'd be too close to their existing pipeline. So we actually had to revise our design to move our pathway farther to the west to ensure that we had enough horizontal separation from the pipeline. And you can see just here signage on the top right showing that there's a ATCO high pressure gas line. So this is our revised design, and you can see that the pathway and maintenance access road has now been shifted farther to the west. This did also require us to rejig our pond design a bit, just to ensure that we would still be maintaining the same volume. So we ended up steeping up our side slopes just to ensure that we could contain the same amount of volume that we needed to, and then also respect the right of way. So lesson learned number 3, pre-construction baselines. So before the construction of this pond retrofit, we did not undertake traffic noise monitoring. But because our project was going to be lowering a berm by 1 to 1.5 meters on the southern border of the site, some residents post-construction mentioned that they had concerns that traffic noise from Sarcee was louder than before. So what we ended up doing is we undertook traffic noise modeling during the construction phase, just to, again, gain a picture of what the noise levels, modeled noise levels would be. As far as noise levels go, for Sarcee Trail, we would be governed by the City of Calgary's Surface Transportation Noise Policy. Sarcee Trail is a designated truck route, and this policy has a maximum 65 dBA, so 65 decibel value for the L10 peak hour. So L10 is the noise exceedance 10% of the time. We were looking at peak AM and peak PM periods, so morning rush hour, evening rush hour, and based on the noise model results, we were well below that 65 dBA threshold. And then post-construction, we also undertook noise monitoring. So one of the residents allowed us to set up a microphone in her backyard, and we undertook 48-hour traffic noise monitoring at 2 occasions, once in October 2017 and then another in September 2018, just to measure the noise levels. And measured noise levels for the L10 peak hour came back below that 65 dBA threshold, and because we were below that 65 dBA threshold, then no noise mitigation measures were required. So that was really good. Lesson learned number 4, I would say on geotech. So when we originally had our pond design, we selected our borehole locations to be representative of the pond footprint. So 1 borehole number 2 at the northern end of the pond, borehole number 3 in the middle, and then borehole number 4 on the southern end. Over the course of the design, our pond design actually elongated. So our pond extended a little bit farther south than that borehole 04. You're seeing here in the figure. We did not elect to drill an additional borehole. And when we were excavating in the area south of that borehole 04 location, we ended up encountering some Brown's mixed waste material that was likely placed there during the West LRT construction. So this was a bit of a issue for us. We had a schedule delay of around 3 days as we were trying to figure out what to do with the Brown's material. We needed to get it tested. Luckily, it wasn't contaminated, so we could have it hauled off to a city landfill. But it did end up increasing construction costs by around $37,000. That was the amount in tipping fees that we had to pay to haul the material to the city landfills. And in hindsight, if we had known that there was Brown's material there, could we have revised our design in a way to mitigate that Brown's material? Maybe we wouldn't have been able to totally eliminate any of the excavation in that area, but maybe we could have reduced it. even more. One thing I will say is the borehole logs did give us a very good estimate of the amount of type A rock that we were going to be encountering in this area. So that proved to be a benefit for us based on our tendered amount and our actual amount. We're very close for the type A rock. And last lesson learned that I'll talk about today is just landscaping. So trying to stay on top of weeding. Weeds grow really, really fast in Calgary. It's hard to stay on top of the weeding. For this site, because it was an off-leash dog area, we were not allowed to use any sort of chemical treatment. It all had to be mechanical, so whippersnipper, mowing to try and reduce weeds. Our original design actually specified a native seed mix, but then we ended up changing that during construction to an urban A, City of Calgary urban A seed mix, which is a faster growing seed mix, so just trying to choke out the weeds. And then later decided to reseed any of the bare areas with urban F. So urban F is a non-mow variety, or mix I should say, whereas urban A is a variety that you do need to mow continuously. Grass is growing there right now. I was at the site last week and everything seems to be filled in nicely. But I guess for the city, it's just a matter of maintenance now because the city has now taken over maintaining this dry pond area and weeding. We did also fence off the pond bottom for the 2 growing seasons, just to make sure that we would have adequate coverage of the grass during that maintenance period. Some residents weren't so happy about that because they wanted to use the off-leash area, which is actually within the dry pond. But now that everything is green and looking nice, some of the residents that I have spoken to are very happy with how this project turned out. So now just a few photos, construction, post-construction. So just looking south right now, we've got Sarcee Trail to our left and Strathern Crescent to our right. So we're grading in the pond bottom. You can see the start of the maintenance access road and pathway over to the left. And then photo on your right is everything post-construction. We've got our planting beds in, we've got the grass growing within the pond bottom area, and you can see we have our maintenance access road and pathway, which are asphalt. Within the pond bottom area though, we ended up using a geocell product and vegetating that just to give it more natural look. So just another photo here. So now we're looking north. So this is during the maintenance period where we had the pond bottom fenced off to allow the vegetation to grow. Photo now shows the traplow. So that Strathern Rise traplow that was around 0.5 meters deep. So previously, photo on the right is what we would have seen during a heavy rain event. So water pooling along the sides of the road, not impassable for this instance, but still a bit of a concern. Different view now of that same event. And then this is the traplow after. So we don't have nearly the same depth of traplow ponding within this T intersection due to that high flow bypass that we introduced into the pond bottom. And then just 2 different views of the spillway. So this is looking east. We just have the standard curb and then a boulevard area by the fence. So before, water would actually pond up above that standard standard curb and then spill over into the pond. And then we haven't seen that occur since construction of this retrofitted dry pond. So the access road, just a little bit about that. So we ended up using a city industrial road standard, so kind of a thicker subbase and base course because of the maintenance vehicles, hydrovac vehicles that would be using the maintenance road. And then as you can see, the maintenance road is shared with the the maintenance road is shared with the regional pathway up in the top left. And then there's a Y intersection where the pathway veers off to the left. And then the maintenance access road continues down on the right into the pond bottom. This is the geocell that I had mentioned before. So geocell was filled with a granular product. So we used gravel to fill in the pockets of the geocell and then use topsoil and seed on top. And as you can see, it's almost seamless. The vegetation growth within the pond bottom and then over top of the geocell is pretty much the same. And that's just a view. I guess we're looking south now towards the bottom of the pond, so the deepest portion of the pond in the south end. Yeah. So photo now is just of the pond side slopes. You do see a bit of rilling going on, so like grooves within the soil for the photo on the right. Those have since been filled in with the vegetation. I believe this photo on the left was taken in late 2017. So the vegetation was still in early stages, still taking root, but it's now filled in. And then just the photo on the right is of one of the planting beds that we have. And we ended up planting quite a few Saskatoon berries in this area. So if you like Saskatoon berries, this is probably a good area for you to go if you'd like to pick any. We also have some seating areas as well, just for pathway users to sit, relax while they're out walking their dogs. And these have been fairly well used during the occasions that I've been up on site and seen people in the area. Emergency spillway. So this is one thing that we introduced for this retrofitted dry pond. The original pond did not have an emergency spillway. This retrofitted pond that we designed included an emergency spillway. One thing I will say, the city did not like the idea of the emergency spillway overtopping the pathway. So you see here, we ended up constructing a rig mat. And then we have the emergency spillway that drains underneath the pathway. So we don't have to worry about water spilling over the pathway. Emergency spillway, if we ever have flows that need to exit the path or exit the pond along the emergency spillway, they'll actually drain underneath the pathway, and pathway users will not be affected. And just another view here of the regional pathway and the rig mat. And that's it for me.
Okay, thank you so much. That was great. I'll just open it up. If anyone has any questions, please type them into the question box in your control panel. Give people maybe just a minute here, but I'm not seeing anything yet. So as with every other presentation, if you guys do have any questions that come up after, please feel free to contact Alicia outside of the conference. And it doesn't look like we have any questions for you. So yeah, thank you so much to all of our presenters for taking the time and navigating this new world of virtual conferences. It was really great. And thanks to everyone who participated today and who attended.
Thank you, Samantha. Job well done. Thanks again to the presenters. Thank you again to all of our sponsors. So we're going to be back online for 2 more talks in about 20 minutes, and that'll be it for today. So hopefully we'll see you for the last 2 talks. Thank you again, everyone, and thank you, Samantha. Take care.
Thanks. Bye-bye.
Yeah, thanks, everyone.